Yes, it's on.
Right? The speaker, yes.
Hello. Hello, my dear. Welcome to IMS GATE Academy. I hope you are all good and your preparation going in a right direction. I am Pragyabrat Tripathi, Faculty, Department of Mechanical Engineering. So, my dear, now today we will discuss the second law of thermodynamics, right? These are the some typical process in which we have to understand what is the process of the thermodynamics. Before that, we will solve some problem for the steady flow energy equation. Okay, what is that? What is the steady flow energy equation? We know that the conservation of energy, that means first law deals with the conservation of energy, right? For the closed system, for the open system and transient system. Okay, the closed system, there is no interaction of the mass, that means energy will interact only in the form of heat and work. But in the open system, the interaction of energy will take place due to the mass of the fluid flow. Now, when the mass of the fluid will flow into the system or exit the system, fluid itself have a stored energy. Fluid itself have a stored energy. That means if there is a fluid at rest or fluid at a motion, in both the situation the stored energy will there, right? But the one extra component will add when the fluid is flow, that is known as flow work, also known as pressure energy. Okay, that work is the specific work, that means work per unit mass, right? That means in the case of non-flowing system, internal energy plus kinetic energy plus potential energy per unit mass basis, that is the stored form of energy. And what is the when the fluid is flowing, so what is the stored energy? Internal energy, kinetic energy, potential energy plus flow work is there. Now the internal energy, the component of energy of internal energy, internal energy and the flow work will combine, and it's combined the form of another property known as enthalpy. So when the fluid is non-flowing, the sum of internal energy plus kinetic energy plus potential energy, these are the stored energy. But when the fluid is flowing, the enthalpy plus kinetic energy plus potential energy is the stored energy. That is clear. Okay. Now, so we'll apply this a conservation energy balance for the open system. So for that one, we have some problem for that one. This is your problem. Okay, this is the GATE 2019 problem. What is that? See beta, this is a gas is heated. First read question carefully. Beta. What is that? A gas is heated, that means gas is heated in a duct, that means there is any duct, closed duct, okay, as flows over a resistance heater, that means in the duct there is a resistance heater. See my dear, there are two things, one is the heating effect and other is the work effect. If the heater we consider as a system along with the control volume, if the heater will count in the control volume, that the effect is a work effect, not heat effect. I will discuss you, no problem. Okay, so there is that means there is any channel, pipe, closed duct in which there is a heating system and the air will flow. Okay, air will flow, gas will flow, not air, gas will flow. Consider a 101 kilowatt of electrical heating system. That means what you are heating, the gas what is heating through a power rating, that is called power rating, is 101 kilowatt is the power rating. Okay, the gas is entered the heating section at the of the duct is 101 kilopascal and 27 degrees centigrade with the volume flow rate it is given. That means this is the discharge. This is nothing. This is the discharge is given. That means if you assume that there is a control volume, the control volume, there is a inlet section and there is a exit section. There have a many inlet, there have a many exit, but in this case only one inlet and only one exit. So at the inlet section the property are given. at the section. This is not at a point. This property, that means pressure, temperature, that property at the inlet section. That means this property is throughout the same at that cross section. So what is the property at the inlet section is 100 kilopascal, and what is the property at in terms of temperature 28 degrees 27 degrees centigrade. Okay, no problem at all. And the volume flow, this discharge is constant. Why? Because we think that the area is uniform. If the area is uniform and fluid is incompressible, we can say that the discharge is uniform. Okay, 15 meter cube per second. Okay, if heat is lost from the gas in the duct to the surrounding, that means during the heating we assume that there may be a heat loss. We cannot assume like that there is an insulated device. Okay, so heat will loss. How much heat will loss? 51 kilowatt is heat will loss. The exit temperature of the gas is assumed, right? So you have to find the exit temperature. That means the temperature at the exit section. Okay, in which situation there must be a 51 kilowatt heat will loss from the control volume system to the surrounding. Okay, no problem at all. There is something is given. Assume the constant pressure, ideal gas, negligible change. That means, see the beauty. This have a constant pressure. That means these are the heating process. The heating, that means what you heating is at a constant pressure. Okay, the heating is at a constant pressure. That means there, when we are heating, see, when the fluid is flowing, there must be a pressure change, but not at that condition. It is not that a pressure will constant. When the pressure will constant, fluid cannot flow. But while heating is a heat exchanger. This is a heat exchanger. Heating, cooling generally will done at a constant pressure. Why? Because the heat exchanger, it is a type of heating device. That means heating or cooling from one fluid to the another fluid, and it will take at a constant pressure. In general, we can design the heat exchanger at a constant pressure. Okay, no problem at all. Now, so what we can do that during the heating process, during the heating to the resistance, this have a constant pressure. No problem at all. Okay, the gas we assume an ideal gas. Okay, Okay, negligible change in kinetic and potential energy. And negligible change in kinetic, that means what is the inlet kinetic energy is the same as exit kinetic energy. What is the inlet potential energy is the same as the exit potential energy. That means change in potential energy, change in kinetic energy is zero. That means system is stationary. Okay, no problem at all. Negligible change in kinetic and potential energy. Okay, and constant specific heat, Cp, it is given. Constant specific heat, the gas have a constant specific heat 1 kilojoule per kg Kelvin, and gas constant, it is 5 kilojoule per kg Kelvin, it is given. So what is the exit temperature? Okay, so this is your question. So once we have to design the duct. Okay, so see my dear, okay, so this is our duct. This is our duct. Let's suppose this is our duct. Okay, this is our duct, beta. Oh, this is little bit longer. Oh, one second. Take this. This is our duct. Okay, so this is our duct. This is our duct. Okay, this is our duct. And there is a resistance heater is there. Okay, there is a resistance heater. Okay, so this is our resistance heater. No problem at all. This is our resistance heater through which we can heat the fluid. Okay, this is our resistance heater. Okay, this is our resistance heater, and the fluid is in. So we can take the control volume like that. Okay, so we can take the control volume like that. What is the control volume? We'll take, this is our control volume. Okay, this is our control volume. This is our control volume. Okay, let's suppose this is our control volume. So we take heater in the part of the control volume. Okay, this is our control volume. This is our control volume. So this is our control volume. This is our control volume, okay? And the heater, this is your heater, okay? This is your heater. This is your heater, okay, no problem at all. This is your heater, where the heat will, this is your heater, okay? Heating system. Now in that one, what is that? There must be a current will flow, okay? The current will flow through a potential difference V. V is the potential difference, okay? The current will flow in. Now, if this heater is inside the control volume, if this heater is inside the control volume, that means the work effect is there, not heating effect. This is the work effect, not heat effect. Why? Because he only, see, if there is a current I, okay, current I, it is flowing, right? And through the current I, there must be a charge. There must be a charge, and that gives the electrical work. That means this current will flow, current will enter to the system. Due to the current, the work effect is there. If this coil is outside, that means if this coil is outside from the duct, during that, what is the gas will heated, that what is the gas temperature will change, that gas temperature change is due to the heat transfer. So in this case, with a mind it, there is no heat transfer is there, only work transfer takes place. Why? Because this device, that means the electrical heater, is inside the control volume. It is not crossing the boundary as a heat, okay? So if we think that, see Vita, this is our one container, this is our another container, okay? This is our another container, okay? Now, if this is our system, see Vita, if this is our system, if we take, this is our electrical heater, okay? If you think this is our electrical heater, okay? This is our electrical heater, okay? This is our electrical heater, okay? This is our electrical heater. Now, if you think that this is our control volume, let's suppose this is our control volume, the system, this is our system, and now we take, this is our system. This is our system. These two are different. If we take, this is our system, if we take, this is our system, that means we disregard the electrical heater as a part of the system. So in this condition, this is, there is also current will flow I. There is also current will flow I. The effect are same. In both conditions, the temperature will change. Let's suppose it will increase. Let's suppose it will increase. But this property change is due to the heating effect. That means the heat will supply here. This is a heating effect. But in this condition, the property of the system will change. It is not a heating effect. It is a work effect. So in this one, there is electrical work. There is electrical work. So in this case, no work effect. Work effect is 0. In this case, the heat effect is 0. And we know that first law of thermodynamics, Q is minus W is equal to delta U. So in this case, first case, W is 0, that means Q is equal to change in internal energy. First case. Second case, Q is equal to 0, that means W is equal to minus delta U. Yes or not? W is 0. And the work is into the system, so there is a minus W electrical is equal to minus delta U. So minus minus cancel. So if we add the energy to the system, internal energy will increase. If we add the system, if you add the energy in the form of heat, the internal energy will increase. So both energy have the same effect on the system. So in the case, both cases, the temperature will increase, either heating effect or either work effect. So in this case, there must be a work will supply. Which work? Electrical work. W electrical dot. That means we take a power, joule per second or kilojoule per second. Okay. So this is our inlet section, and this is our exit section. Okay. The fluid is in here. The fluid is exit here. Okay. The fluid is in here. The fluid is exit here. Now, something it is given, inlet section. The inlet section is section I. section I and section E. Okay, those section, one inlet, one exit. Okay, so it is given how much electrical power it will given. This is your 101 kilowatt will give into the system. Okay, now it says that it will lose heat. Okay, it will lose heat. Okay, it will lose heat. It will lose heat. Okay, this heat will lose. That means Q dot. Okay, why dot? Why? Because this is watt. Watt is joule per second. So we have to do the energy in transfer per unit second, not per unit mass. Okay, so Q is equal to, it is given 51 kilowatt. So mind it, this is per unit second, per unit time. This is not per unit mass. Okay, now so this is given, this heat loss it is given, and the volume flow rate it is given. The fluid which is flowing have a volume flow rate it is given. How much it is given? This is given 15 meter cube per second. Meter cube per second. It is given. Volume flow rate it is given. V dot it is given. Okay, no problem at all. Okay, so inlet section it is given Pi is equal to 100 kilopascal. Okay, inlet temperature it is given 27 degrees centigrade. Exit section it is given, it is not anything, it is given the exit temperature. We have to find it. What is the exit temperature? Okay, we have to find. This is our control valve. Okay, exit temperature. Now, how to find exit temperature? Just think. How to find exit temperature? Just think with us. How to find exit temperature? See, in open system, when we have defined open system, first nothing to do. First you calculate the mass flow rate. Why? Because volume flow rate it is given. First you calculate the mass. How much mass rate, matlab kilojoule per second is flowing. The volume flow rate is given, and the gas is ideal. Gas is ideal. So ideal gas. Okay, ideal gas. And what is the equation of state for the ideal gas? What is the equation of state for the ideal gas? PV is equal to mRT. Okay, P is the pressure in the form of absolute, R is the gas constant, characteristic gas constant, not universal gas constant, and T is the temperature in Kelvin. Always remember. Okay, now if you write, this is your meter cube, volume is meter cube, but there is a meter per second. So dot is there. Put dot here. So this is your meter per second, meter cube per second. So this is kg, so kg per second. These are the balanced. These are the balanced. Okay. From here, so if we find m dot, so this m dot is now kg per second, and this m dot is equal to P into volume flow rate divided by R into T. Now, which temperature and which pressure you have to put? Any of this one. Why? Because mass flow rate is uniform. Mass flow rate is uniform. Why the mass flow rate is uniform? Why? Because conservation of mass principle, we know that mass at inlet, m dot at inlet minus m dot at exit is equal to dmCV by dt. And this device is a steady device. That means the property will not change with respect to time. That means dmCV by dt is equal to 0. That means what is the m dot I is the same is equal to m dot exit. That means mass flow rate is same. So if we put m dot I here, yeah, m dot E here doesn't mean. But what here we put that information which you have a maximum information you can know. So you know the pressure at inlet, you know the temperature at inlet. R it is given, V it is fixed. So you can easily find the mass flow rate. Find it, okay? So from here, we can put Pi, volume flow rate is fixed, R into Ti. Put all this value. Put all this value. What is P? P it is 100 kilopascal. So 100 it is there. Now what is V? V it is 15. What is R? R it is given, yes, 0.5. So see, P it is kilopascal and R it is given beta 0.5 kilojoule per kg Kelvin. It is given kilojoule per kg Kelvin. So this is also kilo and this is also kilo. So kilo cancel will. Okay. So R is must be put in kilo. 0.5 into T. Ti is 27 degree. Convert it into Kelvin. So 27 plus 273. How much? 300. So what is this? This is your 10 kg per second. Kg per second. This is your mass flow rate. 10 kg per second. Okay. Now we can easily apply steady flow energy equation. So conservation of mass for the open system. Conservation of energy for open system. What is that? You have to put any form of conservation. So heat Q dot, we know that Q dot plus Mi dot Hi Vi square divided by 2 plus Zi at inlet is equal to W dot plus M dot exit H exit plus V exit square by 2 plus G. This is the conservation of energy at a section. This is at a section. This is the conservation of energy at a section. And mind it, beta, Bernoulli's equation is also conservation of energy, but that energy at a point. That energy at a point and this energy at a section. Very important. So this is equation. Now, what is it is given? So, according to the question, it is given change in kinetic energy is negligible. That means this and this are cancelled out. Change in potential energy are negligible. This and this are cancelled. So, what is the modified equation? Q dot plus M dot into Hi plus W dot plus Me dot He. See, my dear, see, this is your joule per second, yeah, kilojoule per second. So this is your joule per kg. H is the joule per kg, okay? M dot is kg per second. So kg cancel, this is a joule per kg. So this is also what, okay? Understood now? This enthalpy is joule per kg, specific. This is a specific, that means joule per kg, let's suppose. M dot kilojoule per second. So kilojoule, that means joule per second. This is also what? This is also what? So these all are the energy per unit time basis. That is the energy per unit time basis. Okay. Now, if you divide this one, that means Q dot divided by M dot plus Hi W dot divided by M dot. See the beauty. Plus He. See, my dear, this energy, it is in, let's suppose this is in kilojoule per second. This is your kilojoule per second. And this is what? Kilojoule per kg. This is your kilojoule per kg. This is your kilojoule per kg. This is the difference. This is your kilojoule per kg. Now, sometimes this Q dot by M dot is written as Q, small q, plus HI is equal to a small w plus HE. So this energy, it is in the form of kilojoule per kg. Kilojoule per kg. So this is the energy equation per unit time basis. This is the energy equation per unit mass basis. Okay, put all this value. So this Q, it is given W. Q, it is given heat lost. W, it is given work input. HI, what is we know that HI? HI, H is the enthalpy for the ideal gas. What is that? CPT, Cp into T. This is the enthalpy equation. H, Cp into T. If you write HI, so this is your CPTI, HE, this is your CPTE. Put this value here. Put this value here. Okay. So this is what? So HI, okay. M dot, it is given. This is Q, it is given. Now this Q, this is what? Kilojoule per kg. But here Q, it is given kilojoule per second. This Q, it is given kilojoule per second. So better to write this equation, kilojoule per second. This is your kilojoule per second. This is your kilojoule per second. This is your kilojoule per second. So this equation is kilojoule per second and this equation is kilojoule per kg. Which equation you can apply for the given data? According to the given data. Given data, the heat, it is given, energy, it is given kilojoule per second. So this equation is applicable. Okay. So if we write, put this value, generally you have to find this, you have, this you also you have. If you put this one, this is also, so from this equation, we can take this equation. This is very interesting. First equation. So first equation is what? Q dot by M dot plus HI W dot by M dot plus HE. Okay. Q dot is what? Heat lost if there is a system. If in this system, if heat will out, so this is a negative. If this system, work will in, so this is a negative. So this is the negative, this is also negative. So negative it is given. So heat will out, so minus, how much? 51. How much? M dot? 10. Plus, what is HI? Cp into Ti. Right. W is in. What is the W is in? Minus 101 divided by, what is M dot? 10 plus CPT exact. This is a very intelligent manner. You can solve there is a 0% chance to, what is that? Mistake. So what is that? TE minus TI into CP. This is equal to 101 minus 51 divided by 10. So this is your 5. And we have CP, that means this TE minus TI is equal to 5 by CP. And CP you have it na? 1. See? CP you have 1 kilojoule. Okay. So put, this is 1. So this is a 5. Okay. Now, TI you have. So what is TE? 5 plus TI. So this is 5 plus TI is how much? 300 Kelvin. Put Kelvin. So this is 305 Kelvin. And if there is a 305, option is centigrade, so this is your 32 degrees centigrade. This is your 32 degrees centigrade. So there is a lots of mistake here to apply this energy equation. This is, and apply this negative. How to put energy balance, how to put energy interaction of the system. Okay. So the option is how much? 32. Option is this. A is option correct. A option is correct. So this is a simple example. Okay. And this is your 2019. Now the next is this one. 2018. This is a very intelligent question. Okay. 2011 question. So we can solve this question in two different methods. No problem. This is your converging diverging nozzle. Okay. This is your converging diverging nozzle. What is that? See beta. The temperature and the pressure of air in the large reservoir. So there is a reservoir. There is a reservoir, beta. This tank will connect to the reservoir, large reservoir, and this reservoir have temperature. It is given 400 Kelvin and 3 bar pressure. That means this tank have a temperature. The fluid, what is the fluid present in this tank, have a temperature 400 Kelvin and 3 bar. Okay, respectively. A converging diverging nozzle. That means this is converging and this is diverging. Okay, nozzle it is given. Nozzle at the exit area. That means this area it is given. Exit area it is given how much? 0.005 meter square. Okay, is fitted to the wall. That means this nozzle is fitted to the wall. This is the wall. Okay, this is the wall fitted to the wall of the reservoir. Okay, this is the reservoir and fitted it. So nozzle is the separate part and reservoir is the separate part. We have to fit it. And what is the function of nozzle? To increase the exit velocity. To increase the exit velocity. Okay. What is the function of throttling? What is the function of throttling? To reduce the pressure at a constant energy, constant enthalpy. Very important. We have to know what is the practical application of this device. So nozzle, what is the purpose of nozzle? To increase the velocity at the exit. Number first. What is the function of the throttling device? To reduce the pressure. To reduce the pressure at the same energy, same enthalpy at inlet and exit. That means you cannot sacrifice the energy in the form of internal energy plus flow work at the inlet and internal energy plus flow work at the exit. We want the same in that condition, and also we want that the pressure will reduce. Why? Because we know that when the pressure will reduce, energy also will reduce. But we cannot want that energy will reduce. But we don't want that energy will reduce. So in that condition, if you want the pressure will drop and energy will same, we must apply the throttling valve. Okay. So this is the nozzle, right, fitted to the wall of the reservoir as shown in figure. The static pressure of the air at the exit section. That means at this exit section, what is the static pressure? We can measure the piezometer. We can measure the piezometer. There is a piezometer, we can measure the static. That means if there is a pipe and if you feed the piezometer, what is the fluid will rise in the case of in that piezometer, that rise will measure the static pressure. So the static pressure it is given of the air at the exit section. The exit section, what is the exit section? What is the static pressure it is given? That is the given. Okay. Exit section. The static pressure of air at the exit section for the isentropic flow. This is very important. What is the isentropic flow? That means we don't want that any losses. Isentropic, that means this is the isentropic. If you want the static pressure at the point and the process is isentropic flow, that means the entropy will same at the inlet and exit. That means what is the inlet and what is the exit? The entropy will same. Why? Because the flow is isentropic. Okay. Through the nozzle is 50 kilopascal. That means exit pressure it is given. The characteristic gas constant and the ratio of specific heat R. That means this is characteristic gas constant R it is given, and Cp by Cv, that means gamma it is given. Okay. Now, the density of the air in kilojoule per meter cube, that means if you find the density, that means rho at where? Exit. See my dear. That means if you find the density, if you have to find the information about the density of the gases, density of the fluid, that means there must be a chance that the compressible. That means the density at this point and density, that means density at each and every cross section will change. Okay, so we have to find what is the exit density. Okay, and then we have to find the mass flow rate of air in the nozzle. That means what is the mass flow rate? That means we have to find m dot mass flow rate and density at exit. Now, so in this case, beta, we can take the control volume as a nozzle. That means the nozzle act as a control volume, and these are the isentropic. That means there we cannot assume there is any heat transfer. And nozzle, it is not a working device. We have not play any working. So in that case of nozzle, we can assume that there is no any heat transfer and no work. That is very important. That means if you find that there is a nozzle, okay, so this is our nozzle. This is our nozzle, okay. Nozzle, it is a device to increase the exit velocity, and this is our inlet I, this is our exit E. Okay, and nozzle we act as a control volume. Nozzle we act as a control volume. So it is inlet through the reservoir and exit at the atmosphere. So this is our control volume. One inlet and one exit. And the inlet condition it is given, exit condition it is given. What is that? We'll check. The inlet condition of the temperature it is given, Ti 400 Kelvin. And the pressure Pi is 3 bar. If you convert in kilopascal, this is your 300 kilopascal. 300 kilopascal, okay. P inlet, right. Area at exit it is given. Area at exit it is given how much? 0.005 meter cube it is given, okay. And exit pressure, this is in the form of static, it is given 50 kilopascal, okay, it is given. Now we have to find the exit density is what, and we have to find the mass flow rate. This is also a steady device. That means what is the mass flow rate at inlet is the same as the mass flow rate at exit. This is also a steady flow device. Okay. Now, so we have to find the exit density and we have to find the mass flow rate. How to find? Just think. And see beta, for the nozzle, this is a SI is equal to SE. Entropy at exit is the same as the entropy at inlet. That means this is an isentropic flow. You can call me, call. Tropic flow. And generally isentropic flow is reversible and adiabatic. That means there is no any heat transfer. So in this case, we can assume that no heat transfer and there is no any working device is installed inside the nozzle. So work is also 0. So this is the characteristic of the nozzle. Okay. So how this characteristic we can assume when the flow is isentropic. Okay. Now we apply the steady flow energy equation, energy conservation of energy for the open system. What is that? Q dot plus m dot hi vi square by 2 plus zi at ignite is equal to okay, is equal to w dot plus m dot he plus ve square by 2 plus zze. No problem. This we have. Now there is no any heat transfer, there is no any work transfer. Okay, but we cannot say that there is no any change in kinetic energy or potential. See, we can assume that there is a horizontal nozzle. This is the installed in the reservoir, and generally we install the reservoir. That means if this is a reservoir, so we install the nozzle in a horizontal position. That means what is the difference of the head from the datum level is the same as inlet and exit. So we can assume that this is also 0. So what is the equation? Now the equation is m dot hi plus vi square by 2 is equal to m dot he plus ve square by 2. We cannot take the velocity is 0. Change in velocity is 0. Why? Because the nozzle, the exit velocity is very, very much higher than the inlet velocity. The purpose of nozzle is to increase the kinetic energy at the exit. The purpose of nozzle is to increase the kinetic energy at the exit. Okay. So we have to find. What is that? Now there is no information. It is see. Now this is okay. Now see, this is your this end is placed in the large tank. So the depression, that means the change in the level in the large tank is very slow as compared to the exit velocity. That means what is the inlet velocity from the tank is very, very less than the exit velocity. Why? Because it is installed in the large tank. This is very important. That means if the nozzle inlet will install in the large tank, so the change in velocity, that means the velocity will inlet is much less than the exit velocity. That means V inlet is very, very less than the V exit. Why? Why? Because the inlet section is placed at the reservoir. Okay, so we can assume this is also 0. Approximately this is also 0. Why? Because a reservoir. So what is the equation? So our equation is okay, m dot. Oh, here is also m dot. No, m dot. So here also m dot is there. Okay, multiply with m dot. Yes or not? If you multiply m dot. So here also m dot is there. Okay, so m dot is there now. So this is 0. This is m dot. So we have to divide m dot. So hi is equal to he plus ve square by 2. Because this is the equation of the nozzle. Always remember, this is the equation of the nozzle. Always remember, in general. That means, in the case of nozzle, the inlet exit enthalpy will reduce. See, what is the exit enthalpy? Inlet enthalpy minus exit kinetic energy. That means the enthalpy at the exit from the nozzle always reduce. In general, always reduce when the flow is isentropic. That means, what is the conclusion here? He is less than hi. Yes or not? Yes or not? Enthalpy at the exit is less than. See, enthalpy at the exit is less than the enthalpy at the inlet. Why? Because this is the positive quantity, and you add the positive quantity, inlet enthalpy is always higher than the exit enthalpy. So in the case of isentropic flow through the nozzle, enthalpy at the exit always reduce. Enthalpy at the exit always reduce. Okay, no problem at all. Now we have to put all this value. So there is air. That means what is the fluid? Fluid is flowing. Pressure is the reservoir. The respectively the converging. There is a flow from the air exit. So this is air or what? The temperature and pressure of the large reservoir itna converging diverging exit area is fitted to the wall of the reservoir as shown in figure. The static air. This is air. Okay. Pressure of air at the exit section. Okay. This is the air. That means it acts as an ideal gas. So air. So this is your what? That means Cp Ti minus T exit is equal to V exit square by 2. Yes or not? Put this value. Put this value. If you put this value, Cp is what? 1 cross 10 to the power 3. Yes or not? Why? Because Cp it is given how much? Cp. Cp it is given or not? Characteristic specific ratio. Oh, Cp of the air, we know that approximately 1.005. Cp of the air, we know that 1.005. Okay, kilojoule per kg Kelvin. So it is approximately 1 kilojoule. You do move. That means you convert into joule. 10 to the power 3. No problem at all. So this is 10 to the power 3. What is Ti? 400. What is Ti? 400. What is T exit? We don't know. So T exit we don't. T exit we don't know. And what is V exit? We don't know. So from this equation we cannot solve simultaneously what is the exit temperature, what is the exit velocity. Now how we can solve this equation? So during the flow of nozzle there is an isentropic flow. Yes or not? Yes or not? Isentropic flow, and we know that ideal gas of isentropic flow, we know that T2 by T1, that means T exit by T inlet is equal to P exit by P inlet gamma minus 1 upon gamma. We know that. This is the equation for the ideal gas. What is the assumption of this equation, beta? Anyone can tell me? What is the assumptions of this equation? What is the assumptions of this equation? This is very important. What is the assumptions of this equation? What is the assumptions of this equation? Same idea. Number first, the gas, that's an ideal gas. Ideal gas. What is the second assumptions? What is the second assumption? Isentropic process. Isentropic flow. That means entropy will constant at inlet and exit. And what is the third assumptions? Constant specific heat. Constant specific heat. This is a very important thing. Under these circumstances, we can apply this equation. Otherwise, we cannot apply. Okay. So we don't have an exit temperature, but inlet temperature we have, exit pressure we have, inlet pressure we have. Okay. Put this value in this equation. So what is the exit temperature? TE is equal to 400 into 50 exit and 300 inlet divided by 0.4 divided by 1.4 power. So what is the exit temperature? The exit temperature is 239.5 Kelvin. This is the exit temperature. This is the exit. When we can find this equation? Why? Because when this information we can get when these three assumptions are valid. Okay, otherwise we cannot solve this equation. Okay, right. Okay. Now, so if we put this value if you put this value exit, we can easily find the exit velocity. Okay, exit temperature we have. So if you put this one exit velocity, you can easily find. So from this we can find exit velocity. V exit is equal to 567.98 meter per second. This is our exit velocity. So exit condition we have. Now easily we can find all the things. So exit velocity, exit temperature we can know. We have the information. But whether it is this is helpful to, either we can find this value, then we can find the equation. What is the asking in the question? No. It is not necessary, but we have to find, no problem, for the conceptual build-up. Okay. Now, so we have to find the density. So we know that PV is equal to MRT. Okay. So P, density is mass by volume. So mass, this is a volume, mass by volume R into T. So P is equal to density R into T. So we have to find the exit. So this is your exit, this is your exit, this is your exit. R is constant. So from here we can easily find density at exit, pressure at exit, R temperature at exit. So that we have to find the exit temperature. This method, why? Because if you don't find the exit temperature, we cannot find the density. So put this value here. Exit pressure is 50, R is 0.287, T is 239.5 Kelvin. So this equation is 0.727 kg per meter. So this is an exit temperature. Now, same idea. This is it. What is the mass flow rate? We can easily find the mass flow rate. How it is mass flow rate? We know that mass flow rate is equal to rho1, rho I, AI, VI, yeah, rho2, A2, V2, continuity equation. This is the continuity equation. So, what information we have? Rho2 we have, A2 we have, the rho exit, and V2 you have. From this V2 we have VT exit. That means this is inlet, this is exit beta. Exit, exit, exit. So this is exit condition. So we have mass flow rate. What is the exit density? 0.727. What is the exit area? We have exit area, yes or not? 0.05005. What is the exit velocity? Just now we have calculate. This is the exit velocity. Where is the exit velocity? 567.98. 567.98. 567.98. If you calculate this value, there is 2.06 kg per second. So this is your mass flow rate. Now we have to solve very easily. Without this one, we can solve very easily. So the second method is, what is the second approach? Second approach. What is the second? See, there is a isentropic reversible idea. We can apply PV, small v, power gamma is equal to constant. See the beauty. And what is the specific volume? 1 by density. So, P by density pe power gamma is equal to constant, we can write. So, apply Pi, density I pe power gamma is equal to P exit, density exit pe power gamma. Okay. We know inlet, we know exit pressure, we know up now. we have to find exit density. So we have to find inlet density. What is the inlet density? So from here we can find the inlet density. So what is that? Pi by Pe is equal to rho I by rho E by power gamma. Yes or not? By power gamma. Okay. Now if you apply this equation, only we can bother about the inlet density. Yes or not? How to find the inlet density? Very simple. You can apply this equation. Pi Vi mr Ti. So Pi rho I r Ti. So from here rho I is equal to Pi r Ti. Now you know the inlet pressure given. It is given. And it is also given, this is also given, so you can easily find the inlet density. You can find the inlet density, put here, and you can find the exit density. Very simple. You can find the exit density. Why? Because inlet density, you can find this equation. So only this information you can find the exit density. You can find easily. Now, what is the mass flow rate? So for the mass flow rate, we know that what is the mass flow rate? Mass flow rate is equal to rho I rho exit, because exit area it is given. Rho exit area at exit, V at exit velocity. So density at exit you have, area at exit you have. Now the challenge is, what is the exit velocity? So for the exit velocity, you can apply the steady flow energy equation. For the exit velocity, you can apply the steady flow energy equation. And what is that? This is your. So from here you don't have a inlet exit temperature. So first you can find the exit temperature. How to find the exit temperature? Isentropic, the exit temperature is like that. So you have to exit temperature, you have to exit velocity. Put this one, calculate. So what is the advantage of this approach? Advantage of this approach is to easily find the exit density with the help of inlet density. So first part is very simple. For the second part, you can solve the steady flow. So how can we find the exit velocity? Apply the steady flow energy equation. What is the steady flow energy equation? Hi is equal to He plus Ve square by 2. So Hi and He, difference between Cp Ti minus Te. Ti it is given. Te, from how to find the Te, exit temperature, for the isentropic relation. From the isentropic relation, we can find exit temperature, put that value, and that you can easily find the exit velocity. Once you find the exit velocity, put this value into this equation, inlet exit density. So this will see what is the inlet density. If you compare that one, so inlet density, how much it is inlet density? Inlet density is equal to 2.61. What is the exit density? Exit density, CWT, 0.727. CWT. Exit density will reduce. That means inlet density is higher is the inlet density, but exit density will reduce. That means exit density is very, very less than, that means exit density is very, very less than the inlet density. If the density is high, that means the inlet density will reduce. Density reduce, that means, what is the density will reduce? If the density will reduce, that reduced density will reduce the pressure. If you reduce the pressure, velocity will increase. If the density will reduce, that means intramolecular space will increase. Intramolecular space will increase. When the intramolecular space will increase, we have to expand the gas. If we have to expand the gas, that means pressure will reduce. That pressure reduction of that pressure will going into shoot out the kinetic energy at the exit. That's why the exit density will reduce. The exit density will reduce, that means intramolecular space will increase. And that intramolecular space will increase is showing that the pressure will reduce. And when the pressure will reduce, that reduction in pressure is converted into shoot out the kinetic energy. Shoot out the kinetic energy. Okay? Clear? So today we will stop here. And now in the next session we will try to enter into the second law of thermodynamics, and it will take hardly 1.5 hours, no problem. Then we will enter into the entropy chapter. Okay? Okay? Thank you. Bye-bye.